Okay, these are the 5-3 notes for Precalculus 2, double and half angle formulas. So we continue our exploration of advanced trig formulas with the first good example being sine 2x. Okay, so what if you want to find the sine of a double angle? So the first thing that's extremely important for you to understand is this is not the same as 2 sine x. So bring that with you, get that sort of programmed in your head in the beginning. Just like last section, when there seemed to be a logical result that wasn't true, it's the same thing here. These are not true. This is also the most common issue that students have on exams is they don't quite understand and they say sine 2x is 2 sine x, so don't do so. Okay, so the best way to do this is actually, believe it or not, to derive the sine of 2x. Now, why is that easy? Well, if you remember from our last section, we were able to find the sine of the sum of two angles. Well, sine 2x is the same as the sum of x and x. So hopefully you understand that these two things are equivalent. So if you know that, then just like last time, we can make this u and we can make this v, and we can go ahead and figure out the formula. So remember that sine of a sum is going to be sine, cosine, cosine, sine, and the plus means it's also going to be a plus in the formula. So we're going to get the sine of u, which is x, times the cosine of v, which is also x, plus the cosine of u, which is x, and the sine of v, which is also x. If we look at these two quantities right here, these are exactly the same quantities. So we can rearrange them and put both of them are sine, cosine, whatever you like, but either way, we have two of them. So our formula is the result, which is 2 sine cosine x. So you can see right here, we have this as our first formula in our gray box over here. Okay, so if you can also do the same thing for all the other formulas. So for cosine 2x and tangent 2x, you can change them into cosine and tangent of a sum, which is here and here. And then if you do the same concept and work out the formulas, you're going to end up with the formulas for cosine 2x and tangent 2x. They are located here, and that you will be using them or applying them in example problems. Now, just a small note, you'll see that sine and tangent to double angles just have one formula. Cosine 2x actually has multiple formulas, not because it's any different than the other ones, only because within these formulas you actually have cosine squared and sine squared. So the two formulas down here are actually variations of our very famous identity, sine squared plus cosine x squared is equal to 1. So if we solve for one of those, let's say cosine squared equals 1 minus sine squared, and then plugged it into the formula, we would end up with one of the formulas on the bottom and vice versa. So just realize that these are variations of that same formula, but in reality, the primary one is the top one, this one over here, that I often use when in examples. So the big thing is we'll be sort of applying this in examples. So what's the best way to do so? Why don't we just do an example of this one right off the bat here? So if you look at number 1, it says use a proper double angle identity to find the exact value of sine 120, given that 2 times 60 is 120. Okay, so if we went down here, it said let's find the sine of 120 degrees. They're saying, well, what we know that that's the same as this, 2 times the sine of 60. So if you look at these two quantities here and here, sine 120, sine 2 times 60, they're the same thing. So if we really look at this in a clever way and go, all right, well, let's do the formula here. It appears that x is 60 in this problem. So if we look at the formula up here, sine of 2x, it appears that's the case. So if I was to just do like a simple formula, if I write this out, so this is the same as this, right? So then we can go up to the formula up here and go, okay, we have to replace 60 wherever we see x in our formula. So if you look at the blue and the green, the two formulas, you can see this is an exact match, which means that from this standpoint, we can go ahead and figure out the actual quantity here. So remember, 60 degrees is the same as, in radian form, pi over 3, and that is the coordinate 1/2 root 3 over 2, right? So if we do 2, the sine of this value would be y, which is root 3 over 2, and the cosine of the value would be x, which is 1/2. So if we multiply this across, we'll get 2 3 over 4, which is the same as root 3 over 2. So the sine of 120 is root 3 over 2. Now note, this problem could have been done using a regular unit circle because 120 is actually a family member of the pi over 3 family. It's actually going to be 2 pi over 3. So just so you know, it could have been done otherwise, but there are other problems where it could not have been done otherwise. I'm just using this as an example of the result. Okay, so just like when we had double angle identities, we also have half angle identities. These are much more complicated looking, and we'll talk about that in a second, but basically you'll see that the formulas are given to you. Each one of the formulas has a plus or minus with a square root. This causes some other issues down the line, only because you have to determine whether it's positive or negative prior to the problem normally. But if you look over at the tangent values, similar to cosine above it, there's actually multiple formulas here. I recommend using just this formula right here as the tangent of x over 2. Just based on my experience with what I've done in the past and these values, this is usually the best one to use to avoid any major algebra or computations involved with it. So basically, these are the formulas we're going to use. We're going to treat them the same way as we did with the other ones. I didn't do any derivation for these just because it's much more complicated, but these are the formulas you are going to use. So for example, if you look at number 2, it says use the proper half angle identity, find the tangent of 15 degrees given that 30 over 2 is 15. Now, in the end of the prior problem, you might have noticed that I mentioned that you could find the sine of 120 directly. Well, you can't with the tangent of 15. So worth noting that this is a problem that is a good one for an exam because you absolutely must use this formula to figure this out. So how do we do this? Well, again, tangent of 15 is the same as the tangent of 30 over 2. Okay, so we look at this and say, okay, well, if we go up and we take a peek at the formula for tangent of x over 2, if you use the formula I stated would be the most wise one to use, you would end up with this formula. So all we have to do is look at it and say, well, clearly x is the same as 30 here, so anywhere we see x, we want to place 30 above it. So we got 1 minus cosine of 30 over the sine of 30. Okay, so we just have to evaluate. Remember, 30 degrees is the same as pi over 6, which is our root 3 over 2 1/2 coordinate. So if we want to do the cosine of that, then that's going to be the x coordinate, which is root 3 over 2. And the sine of it's going to be the y coordinate, which is 1/2. And note, again, just like in the previous round, these are all in quadrant 1, so everything is positive. That's not always going to be the case, but in these example problems, there are. So note that we are to the point, hopefully you're learning about this a little bit, we're to the point in the problem which is similar to a problem we did in the last lesson, which was called a complex fraction. So hopefully there's some bells ringing where you go, okay, how did I solve that complex fraction? Well, or simplify it. We don't want fractions within fractions, so we have to edit this. the best way to do, again, is to find the LCD of every fraction in the complex fraction. It looks like that's going to be 2. So if we multiply everything by 2 over 2, which, by the way, does not change its value because 2 over 2 is equal to 1, but if we multiply everything by 2 over 2, we're going to distribute 2 to both quantities. We're going to get 2 minus root 3 over 1, which is going to give us 2 minus 3 as the exact value of the tangent of 15. Okay, the most common problems that you'll be asked about in the double and half angle section are on this page. So just take a note that this is the emphasis of your studying will mostly be here. So it says for number 3, given that the sine of theta is negative 3/5 and theta is in quadrant 3, find all of the following. So I purposely did a section here that included every single one of the formulas and how you find them, hence why this is such an important page. Note that we start with a concept that we have seen a lot of already, and you might have remembered me mentioning that you want to be very clear and understanding with this, being able to draw these triangles. But you'll notice I did give you a picture over here. This is not a unit circle, but this is just a typical, graphical version of drawing this picture. So it tells you that we have a rotation in quadrant 3. And if we have a rotation in quadrant 3, we want to make a right triangle out of it. And we know that opposite over hypotenuse is 3 over 5. So sine is opposite over hypotenuse. So if we're using this as our theta, then opposite is 3. We know it's got to be negative because it's going down, and its a hypotenuse is 5. The radius is always 5. Then we get this. So hopefully you recall 3, 4, 5 triangles here. So that means this side over here has to be a 4, but has to be negative because we're going left. So we have now filled in our triangle. Note, this has to be perfect because you cannot even continue with the rest of the problems unless you can do this. So just be aware of that when going through the problems. It is a big deal. So what we do basically is we continue on and find the double and half angle evaluations for each of the trig angle functions using this picture, essentially. So sine of 2 theta. If you look at the sine of 2 theta, we know the sine of 2 theta is equal to 2 sine theta cosine theta. Okay, so we go over to here real quick. Remember this? 2 sine cosine. So all we have to do is fill in the pieces as we go here. So the sine of 2 theta is going to be 2 sine cosine. So the sine of theta, if you look at the picture, is going to be, again, negative 3/5, which actually was given to you originally in the problem. The cosine of theta is going to be adjacent over hypotenuse, which is going to be negative 4/5. Therefore, if you multiply all of this out, you're going to get, just remember, I'll put this here, just remember this is over 1. So you're going to get 2 times 3 times negative 3 times negative 4, which is positive 24. And then 1 times 5, which is 25. So we're going to get 24/25 as the sine of 2 theta. So to be clear, this is not the same as 2 sine theta, which doesn't make any sense. Okay, so the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And just to be clear, so if we go up here, you can clearly see that is right here, right? So we're going to move on with that. So if we take a peek at how we accomplish that, we're basically going to find, and just a note here, I just want to point this out. So this is the same as cosine theta quantity squared, and this is the same as sine theta quantity squared. Okay, so these are the same thing. So that means all we have to do is find the cosine of theta, which we already know is here, negative 4/5. And the sine of theta, which we already know is given in the problem, negative 3/5. And we need to square both of them. So to find the result, we do so, we're going to get positive 16/25 minus positive 9/25, and we're going to get 7/25 as a result. Take a really good look though right here at this situation. So be very careful here with order of operations. A lot of students will make this a double negative and make it a positive. Note that's going to end up in a different answer. Be very careful with that. Remember, you do exponents and parentheses first before you start messing with multiplication, which is what a double negative is. So just be careful of that in these problems when you're doing them. Alrighty, tangent 2 theta. Alright, so the formula for tangent 2 theta, if you can flip back on your own and look, I'm just going to write it down here so you don't get crazy nauseous looking back. Me sliding the screen up and down. So 2 tangent theta, 1 minus tangent squared theta. So all we have to do is fill this in. Right, we don't have any tangent so far, so we have to go back to the diagram in order to see what this is. Remember, tangent is going to be opposite over adjacent. So we're looking at -3 over -4, which is 3/4. On the bottom, we're doing 1 minus, but then we're doing 3/4 squared as our result. So we could multiply this top and get 6/4, but we could also reduce the 2 and the 4 to get 1 and 2. So this is 3/2 on the top. 1 minus on the bottom, 3/4 squares is 9/16. Use a little calculator work or not, but 1 is the same as 16/16 minus 9/16 is 7/16. So right now we have this. Okay, remember if you divide by a fraction, you can multiply by its reciprocal. That's one way to do this, or technically this is a complex fraction, so we can multiply top and bottom by the common denominator. Note that would be 16. It really doesn't matter what you do here in order to accomplish that, but let's say I just did this because I know you guys know how to divide by, multiply by reciprocal. So let's say I just did that. So 3/2 of 16 is 24, and 7/16 times 16 is 7. So we're going to end up with 24/7 as our result. Okay, so it says D, use your results from A to C, all right, A to C, to verify what quadrant 2 theta lies in. Okay, this is an interesting one. So I find that students are often very confused about this whole double angle thing when it comes to where it lies. So just to be clear, right now we have an angle theta that has been rotated into quadrant 3. So here's your theta over here. It's been rotated into quadrant 3. So when we're looking at this, we're like, all right, how do we basically accomplish what's going on here? So part of the issue with what we want to make sure we can do is just a matter of looking at where double that angle would fall into. So think of it this way. So if we went into quadrant 3, it's basically somewhere after 180 degrees, but before 270. So that means double that angle would be somewhere on the opposite end of the unit circle, or any circle. This isn't a unit circle, but any circle. So if we're looking at 2 theta, we can think of it that way, but what's interesting about it is we actually know what quadrant this is in, because if you look at the answers for A, B, and C in these scenarios, what are we looking at? We're actually looking at all positive ratios. If the sine, cosine, and tangent of anything is positive, all of them, that means it must fall in quadrant 1. So in this scenario, just realize that that has to be the case here. Okay, similarly, if you look at, it says if you know that theta is between 180 and 270, which by the way, we know it's between 180 and 270 right now, what quadrant must theta over 2 fall into? Okay, so basically theta over 2 must be between what 2 values? Well, if theta is between 180 and 270, then theta over 2 is between half of the other ones. So that means it's got to be between 90, which is half of 180, and 135, which is half of 270. So we know right before we start that theta over 2 in this problem is going to fall in quadrant number 2. Believe it or not, the knowledge of where theta over 2 falls is actually going to be a big deal for these problems, because if you recall, the formulas over here for sine of the and cosine of the half angles actually have plus or minuses in front of them, which means we're going to need to know what quadrant it falls in to pick the correct sign, S-I-G-N, for that scenario. So let's start doing our half angle calculations so you see what I mean. So the sine of alpha over 2, according to our formulas, is equal to the plus or minus square root of 1 minus cosine theta over 2. Okay, so what did I mean in the beginning here by the plus or minus is important? Well, this half angle that we're dealing with falls in quadrant 2 in this problem. So in quadrant 2, you can clearly see that sine is positive, which means we know right off the bat that we're going to end up having a positive result, and we're basically going to ignore the negative or remove it. This is important. So literally in the beginning here, we needed to do this calculation in order to figure that out. And you'll see as we move on, you'll be able to do that again with more practice. But so we now know the result is positive, so we can go ahead and just stick with 1 minus cosine theta over 2 positive version. Okay, so again, we already did all these sines and cosines, but let's just say you forget. So if you return to the picture over here, it's theta over here. Theta is, remember, a cosine is adjacent over hypotenuse, which is going to give us negative 4/5 as our fraction that goes in here, and that's going to be over 2. Now it looks like we have some work going on here. We have to figure out. So clearly over here, this is going to be 1, there's no exponents, so it's going to be 1 plus 4/5. So that's 5/5 plus 4/5, which is 9/5 as our quantity. If we divide by 2, it's the same as multiplying by a half. So 9/5 times a half is going to be 9/10, which is going to be the square root of 9 over the square root of 10, which is 3 over root 10. And as you know, the only way to give this as an answer is to rationalize. No conjugates or anything. This is an easier calculation. So we are going to get 3 root 10 over 10 as our result. And to reiterate, it must be positive because the half angles for this problem fall in quadrant 2. So the sign has to be positive. Okay, the cosine of theta over 2 is going to be plus or minus again, this time 1 plus cosine theta over 2. Now note in this problem, theta over 2 again is in quadrant 2, so if we go to quadrant 2, cosine is actually negative there, which means for this problem, this answer is going to be negative. So we want to make sure that we follow through in this problem with a negative. So cosine theta, we already said, was negative 4/5, that's not going to change. Okay, so we have to do a little bit of work here. So this time, instead of 1 plus 4/5, it's 1 minus 4/5. So 5/5 minus 4/5 is 1/5 all over 2. Again, if we divide by a fraction, we multiply by our reciprocal, and we're going to get negative the square root of 1/10, which is equal to negative 1 over root 10. And if we rationalize, we are going to get negative root 10 over 10 as a result. Again, it's negative because cosine is negative in quadrant 2. Okay, lastly, we got tangent of theta over 2. If we go back, remember there are 3 formulas, but I did suggest using this one. I would listen to that just because it will provide less work for you, most likely, along the way. So 1 minus cosine all over sine. Okay, so what is different about this right away? There is no plus or minus, which means that we don't have to worry about that. with tangent of alpha over 2 or theta over 2, as long as we use this formula, that means the answer will take into effect whether it'll be positive or negative along the way. And worth noting, we already know the tangent is negative in quadrant 2, so we are going to get a negative answer, but the math is going to help us with that. So let's do the math here. So cosine of theta, we've done several times here, is negative 4/5. Remember, the sine of theta was actually provided in the beginning. Sine of theta is negative 3/5. So we got that. Okay, so at the top here, again, we're in a scenario where we're doing 1 minus a negative 4/5, which is 9/5. And then that is going to be negative 3/5. Okay, so we could again do divide by a fraction, multiply by a reciprocal, or we can multiply by the LCD of both of these guys, both these fractions, which is 5. We could also just cancel out the 5s, whatever you want to do. We're going to get negative 9/3, which is equal to negative 3 as a result, which is indeed the negative that we expected for the problem. Okay, so as I always do, I want to show you where students often go wrong with these problems, especially in terms of signage. They get they get very confused. So if you look at what I did over here, all I did was redraw the picture over here without the sides. The key is that it's in quadrant 3. So remember, our theta is in quadrant 3. So what students often do is they go, well, since I'm in quadrant 3, that means my answers for sine, cosine, and tangent should be based on the fact that only tangent should be positive here. So they'll think that these two must be negative and this one must be positive. Well, just realize that this is taking the sine, cosine, and tangent of double the angle. Double the angle is not in quadrant 3. We already know it's in quadrant 1. We did the logic of that. But generally, you just want to be very careful, because even if you're concentrating on an exam, you might end up, making a mistake there because you're thinking of the original stuff. Remember, this is where the double angle lies, which you don't have exactly just by looking at it, but once you find the answers, you can see clearly that it's going to be in quadrant 1 because they're all positive. Okay, so let's do a smaller example of the problem we just did, just so you can understand, how to apply this in unique scenarios. So it says, given that secant of theta is equal to 3 over 2 and theta is in quadrant 4, find the following. Okay, you'll see that we have two problems that we have to do, or two trig evaluations. But before we do that, of course, again, we want to set up a scenario where we have an angle in quadrant 4. Okay, according to this, the secant is 3 over 2, so ideally you want to just change that to cosine. Theta is 2 over 3. Remember, it's a reciprocal function, so we just flip the fraction. And that means adjacent over hypotenuse is 2 over 3. So in our triangle, our adjacent is 2, our hypotenuse is 3. Therefore, we can use the Pythagorean theorem in order to figure out what this value is going to be. So 2 squared plus x squared, we're going to get 9 is equal to 4 plus x squared is 5, and x is equal to plus or minus square root of 5. Okay, so which one is it? Well, it's got to be negative root 5, because we are going down in order to get down to the coordinate. So what does that mean for us? Well, we have the triangle we need, so we just have to follow this ratios. Now, the main thing here is we have two problems, right? Just to be clear, so you cannot figure out what the actual sine of a double angle is before the problem, but you don't really need to, because the formula itself is going to do it for you. For a half angle, you can figure out what it's going to be before the problem based on the calculation we did before. But because this is the tangent one actually sorts that out by just doing the calculation itself. If it was sine or cosine of theta over 2, then we would have had to have figured out before the problem. I'll get into that as we go through it. So cosine of 2 theta. So basically, this is the same as cosine squared theta minus sine squared theta. So all we have to do is sub in the values for cosine, which is provided to us as 2/3. And then we have to go to our triangle to find sine. So we have theta here. opposite is going to be negative root 5 over hypotenuse, which is 3. Got to square it. Remember, again, this is not a double negative. We have to follow order of operations first. So we're going to get 4/9 minus 5/9 is negative 1/9. Okay, so if you look at the next problem, tangent of theta over 2, we're basically just going to apply the formula. But what I want to mention offhand here is because it's a half angle, we could find what quadrant this is going to be in right off the bat. So why don't I'm just going to practice that, even though with the tangent version you don't need it. I just want to practice it. So for example, so if it's in quadrant 4, that means we're starting at 270 and we are ending theta at 360, which means that theta over 2 is going to be between the half value of both of them. Okay, between 135 and 180 degrees. So when we look at this, we can immediately see that the half angle is going to fall in quadrant 2. So we know this angle falls in quadrant 2. And with all students take calculus, we know that the answer must be negative. Now, again, to be clear, if we had been using a sine or cosine of theta over 2, we must do that to figure out the actual sign, SIGN, of the ratio at the end. For tangent, remember tangent was a very unique formula of 1 minus cosine over sine, so we don't have to determine the actual sign, SIGN, of the formula. It's actually going to show for you. So I'll show you how that works. So 1 minus, well, the cosine was given again, 2/3. And we know that the sine was negative root 5 over 3. All right, if we do the math, this is 3/3 minus 2/3, which is 1/3. This stays negative root 5 over 3. We can cancel out the 3's. We can multiply by 3 over 3, whatever you want to do. We're going to end up with negative 1 over root 5. And of course, what you've been doing for a while now, you have to rationalize that. So we're going to end up with negative root 5 over 5 as our answer. So to be clear, notice the answer is negative. So the problem sorted it out for you, whereas if it was sine or cosine, it wouldn't sort it out for you. So you would have had to have done this computation in order to determine what the sign would be for that calculation. Okay, so how about an identity verification problem using these formulas? You know, everybody's so excited about that. So let's try one of these. So interestingly enough, it looks like the right-hand side is the more complicated side here. So let's rewrite that as sine 2 theta over 1 plus cosine 2 theta. Okay, right away you can see that we have formulas for both of these, so we might as well just get right into writing them. So sine 2 theta is 2 sine cosine, and cosine 2 theta is cosine squared minus sine squared. Okay, so just a couple notes here. So right in the beginning here, because of these signs right here, SIGNs, the addition and subtraction, we cannot simplify anything in this problem. So be very, very careful here. No simplifying. So also, everything's in sine and cosine, which means the only thing left is really, is there some type of identity going on here? And there is. And you should look no further than the denominator, where we have some cosine squares and sine squares. So maybe the initial sort of instinct is to look at this and go, hey, isn't that the Pythagorean identity? It isn't, because it's minus, not plus. But there's something to take note here. If you recall, we did a problem a while back where, it could have been last section, a couple of sections ago, where we took the Pythagorean, the trademark Pythagorean identity, and we said, well, what if we actually solved for one of the squares? So example, let's say if we solve for sine squared and we got 1 minus cosine squared theta as our result. So this guy right here. So that means we should be able to put that right in there right now. in order to get what we need. So let's do it. 2 sine theta cosine theta. We got 1 plus cosine squared theta, and then minus, be careful here, in parentheses, 1 minus cosine squared theta. Why do we need parentheses? Well, I hope you realized why right off the bat here, is that we have to distribute that negative to both of these, or we are not going to get what we need out of this. That is just standard algebra rules. So copy that, get 1 plus cosine squared theta minus 1 plus cosine squared theta. Okay, moving on. So again, copy the top. 2 sine cosine theta. The ones actually, looks like they cancel each other out, and we have 2 cosine squared theta. So that's 2, cosine squared theta. So if you look at this, we have something nice going on. It looks like now that everything is multiplication and division, we can start canceling things out. So the 2 and the 2 become 1 and 1. We have a cosine here, and we have 2 cosines there, or cosine squared. So that becomes a single cosine. So if we see what's left over, we get sine theta over cosine theta, which of course is, ta-da, tangent theta, which is our left-hand side. Okay, so the last part of this section is actually one of the more complicated things that you're going to do in this class. Just take a note, I do not put this on exams, but you will have to use this as a guide for a lab problem that you do. Why do I do that? Well, this is actually a Calc 2 application. It's not that it's taught in Calc 2, it's just that in order to do some of the problems that you get to when you get to that course, if you get to that course, you will have to use a power-reducing formulas to make life easier for yourself. Now, the reason why you make it optional in the exam is not everybody's going to Calc 2. Actually, maybe I don't know what the percentage is, but it's not the majority. So I leave it off the exam based on the difficulty level and how hard it is to get through doing an exam problem, or how long it'll take. But I do have to teach it, and it will, so that you have an introduction to it, and you will have to do part of it on the lab. So let's take a peek at this. So you'll see here sine squared theta. So there are times in calculus where it is extremely beneficial if you reduce the exponent so that it's not any value other than 1. So if you have a sine squared theta like you do right there, it is actually equal to this expression, which happens to have a double angle in it, by the way, but that's not important now. But notice there is no square term in the trig function anymore. Well, why is that important? Because when you take, let's say, the integral, which you don't know anything about yet, but when you take the integral of something that has a square, it becomes a very complicated problem with trigonometry, whereas if you look at a problem, if you look at 1 minus cosine 2 theta over 2, it actually is not complicated. So that's why you do it. But the key is knowing the formulas and how they're going to work, and how you can apply them. That's going to be what we're going to do. So you'll see cosine squared theta is almost identical, except its sign is different. So you don't have to memorize these, obviously. So it's just taking note that they are different. So one small thing that I want to add on to this. So I'm just going to put like a little thing here, and you can do the same thing. So what if you were given something like this, sine squared 2 theta? So a double angle square. This isn't as bad as you think it would be. Basically, we can, if you look at the original sign, there's a single theta here, and now there's a double theta. So all we have to do is put the double theta right here when we do the calculation. So watch. 1 minus cosine 2 double theta over 2. And if you multiply that, that's actually equivalent to 1 minus cosine 4 theta over 2. So that's actually right. Same thing over here. If you have cosine squared 2 theta, that's the same as 1 plus cosine 2 times 2 theta over 2, which is 1 plus cosine 4 theta. Now, these formulas you're not going to really be doing that per se, but knowing this is very helpful. And of course, just to be clear, if I ask for the sine squared of 3 theta, this would be 1 minus cosine 6 theta. If it was a sine squared 4 theta, it would be 1 minus cosine 8 theta all over 2. So just to be clear, you'll be doing that in the scope of the problem, but something to take note of in terms of the problem. So let's talk about the actual problems that you're going to be working on. Okay, so let's look at the process for this next problem. Now, this is a very long process. There's lots of explanation involved, hence why, again, it's only going to be on a lab problem. Sine 4x, so let's take a peek at that. So remember, the goal of the problem is to change it so that it does not contain powers of trig functions greater than 1. So we have a 4. We got to get that down. So first things first. Sine to the 4th is the same as sine squared. Squared. Makes sense, right? So why is that important? Because if you look up here, sine squared theta, or x, is the same as this quantity, which means we should put it right in there. So we're going to get 1 minus cosine 2 theta over 2 squared. Okay, so in order to make this run more smoothly, what we want to do is we want to separate this quantity into 2 quantities. So we want 1 minus cosine 2 theta to be 2 elements. Well, how do we do that? We just put both quantities over 2. Okay, and ideally we also want to change this quantity to 1/2 cosine 2 theta. Hopefully everybody sees that these are the same things. So we're going to get 1/2 minus 1/2 cosine 2 theta. All this is doing is making your life much easier as we go. And again, just to be clear here, these are not thetas, these are x's. Every time I plug in formulas, I always, these kind of formulas, I always change variables. So what are we looking at? So we have to square this. So again, back to algebra. If I did something like that, then what is that equal to? That is equal to these, which means I have to FOIL. So I have to FOIL this guy. So let's see what that looks like. I'll do it over here just because it's really pretty gross algebra. So let's take a peek. All right, so we'll FOIL this. First term looks like it's going to be a 4th. Looks like the inside and last terms are the same. So you're multiplying 1/2 times 1/2 negative 1/2 cosine 2x, getting negative 1/4 cosine 2x, and again 1/4 cosine 2x. And then last, we're going to get a 4th squared, which is a half squared, which is a quarter, negative a half squared, and then cosine 2x squared, which is cosine squared 2x. Okay, so finally, which we can put over here, we're going to get a 4th. The 2 middle terms, a 4th and a 4th, make a half, so minus 1/2 cosine 2x, and our last term is plus 1/4 cosine squared 2x. Okay, so moving on here, if you look closely, cosine squared 2x is very similar to this, except it has a double angle. Well, I showed you how to do that here. It just so happens we did it out already, and we ended up with this, which means all we have to do is replace that with this. So here we go. We rewrite everything else, a quarter minus 1/2 cosine 2x. And then we have plus 1/4. Let's do green so you can see what happened here. So then we have to put in 1 plus cosine 4x over 2. Okay, again, we do want to distribute this, but you know what, why don't we just distribute it now? So we'll just multiply these, get 1/4 minus 1/2 cosine 2x, plus 1 plus cosine 4x over 8. So just multiply these two right here, get 8. So then a little bit more simplifying. So we're down here, 1/4 minus 1/2 cosine 2x. Then if we split this up into 2 pieces right here, we get plus 1/8 plus cosine 4x over 8. Note, hopefully everybody's realizing right now that we have no exponents that are larger than 1. That is tremendous. That is exactly what we wanted out of this problem. But we do have like terms. So 1/4 and 1/8, we can add those. So that's 2/8 and 1/8 is 3/8. We have 1/2 cosine 2x. And then this we can change to 1/8 cosine 4x for our scope of problem. So believe it or not, this is the answer to the problem. So if we were to rewrite sine 4th x so that it had no powers that are bigger than 1, it would be this. And then for future reference, for those of you who are moving on in Calc 2, when you get to Calc 2, you'll be able to integrate this very easily, whereas sine 4th x is terrible to integrate. So I know you don't know a lot of those words yet, but that's basically what this is all about and why you're doing it. Remember, it won't be on an exam, but it will be on your lab. You'll have to do the same thing for cosine 4th x.